before we start today's topic, I want to define a couple of terms. The first term is equilibrium. Remember, it's from sometime in the past, maybe even from chemistry class, maybe not even physics, what the word equilibrium is. It's like a balance. That's the word that comes to my mind too. It's a balance. What's the word static? Yeah. Not moving, right? If you take engineering in university, one of the courses you might take in your first year is called statics. Statics is the study of stationary things. So you might be analyzing forces on bridges. A bridge that's not moving, hopefully. As opposed to dynamics, which is the study of things that are moving. And maybe you'd be analyzing planets or trucks or something like that. Static equilibrium, not moving, balance, in the context of electric charges, refers to that state that's occurred, that balance that's occurred when charges stop moving around. Now, the context of this is going to relate to objects that are conductors. Conductors, because this isn't going to happen on insulators, it's only going to happen on conductors. Charges on conductors that are moving around because of repulsion. If you have a whole bunch of electrons on a conductor or in a conductor, for whatever reason, maybe it's because you rub that conductor against your hair, maybe it's because that conductor was struck by lightning or something discharged through that conductor. It doesn't matter what the reason. If it's got extra electrons, those electrons will repel each other, and they're going to move around all over the place for a while. Until at some point, they're going to reach a point of static equilibrium. They repel each other until at some point the forces all balance. It's kind of like you guys. Okay? You get 20 of you guys in a classroom. You guys haven't showered in 5 days. You all kind of smell a little bit. You repel each other. And you don't want to be near each other. So you push each other away, kind of, right? But as you get pushed away from this guy who smells a lot, then it's like, oh my goodness, then I get closer to this guy who smells a lot. So then I go over here, and then there's this guy that smells a lot. And then I go over here, and so on. At some point, you can minimize the amount of smell. At some point, you're going to be somewhere not moving, hoping nobody else moves, so that things don't smell quite as bad. Does that make sense? You're in a point of equilibrium, a static point of static equilibrium, when the forces of repulsion between you and all those other people that smell have balanced. Well, electrons do something pretty similar. They repel each other electrically. They're going to keep moving away from each other until the forces are all balanced. Until the force caused by that electron balances the force caused by that electron and that electron and that electron. In other words, there's going to be a point where these electrons stop moving around. You reach that point of static equilibrium when the forces balance. Excess electrons will always eventually try to balance it. We're going to look at a few different shapes of conductors today to see what the distribution of charge looks like. Okay, if we could physically see these electrons in these conductors, what would it look like? What would the pattern look like with different shaped objects? The first shape that we're going to look at is the solid conducting sphere. It's like a ball. It's like a steel or a copper or a silver marble. Solid conducting sphere. And you can see in the diagram here that we've got drawn 3 electrons in that solid conducting sphere. We've got 1,000 electrons drawn there, or 10 million electrons drawn there. It just makes our diagram a lot more complicated looking. We've got 10 million electrons. The same analysis would apply. What I want to do here, guys, is label these electrons, electron 1, 2, and 3. This, by the way, doesn't mean that you only have 3 electrons in this conductor. It means you could have 3 excess electrons. 3 electrons beyond the number of protons. Now, I want to look at charge number 1 here. Charge number 1 experiences 2 forces of repulsion as a result of 2 and 3. The first force of repulsion comes from number 2. Charge number 1 gets pushed away. We're going to call that E2. Force caused by number 2 down this way. The force caused by number 3 is going to go this way. not E2, that should be F2, right? The force caused by number 2. This is going to be F3, the force caused by number 3. Now the net force, as a result of those two forces, exactly, is going to point outwards like this. It's in between F2 and F3, right? Let's take a look at charge 2 now. Charge 2 experiences a force this way caused by number 1 and this way caused by number 3. The net force on charge 2 ends up being this way, in the middle of F1 and F3. Same deal with the third charge. You get a force this way caused by number 1 and this way caused by number 2. The net force is in the middle and it's going to be this way. What happens now to all three of these charges as a result of these repulsive forces? These net forces that are acting outwards. If you got a net force on charge 1 acting outwards, where's charge 1 going to go? Outwards, toward the surface. And you know what? It goes right to the surface. It doesn't stop. It doesn't go beyond the surface. Even though you still have outward forces acting on it, it doesn't go beyond the outer surface. Not normally. How come? Why do you think it would stop at the surface? It's pushed out by this blue force, which is the combined F2 and F3. It gets pushed out to the outer surface, and even though that blue force still acts on it, it doesn't go beyond the outer surface. Yep. No? It's a good guess, though. Yep. Force not great enough to do what? Like you're on the right track here. The force is great enough to push this electron through this solid conducting sphere. The force is not great enough, Justin, as you said, to go from the solid conducting sphere to the insulator out here. Now, sometimes the force is big enough. If you got a huge buildup of charge, the force of repulsion is big enough to push the electrons beyond the conductor and past the outer surface. That's when you get discharging. That's when the electrons from these things leak off into the air. And sometimes you hear that, right? Sometimes you can physically hear static discharge. That's when the charge is built up to the point where the force of repulsion pushes them beyond the conductor and into the insulator. But it takes a lot of electrons to create that much repulsive force. Make sense? This is what it looks like after all is said and done. The charges go to the outer surface, and if you look at this, the charges end up being evenly distributed. You get a solid conducting sphere with extra electrons. The charges will go to the outer surface, and they will be evenly distributed on the outer surface. All right, let's take a look at another picture here. This one is of a solid, flat conducting plate. Again, a conductor, but this time it's plate, flat, not rounded. It's uniform. It's a nice, even shape, like the sphere was, but not at all the same shape. We'll look at the first picture here. We've got three charges. Let's label them once again, charge 1, 2, and 3. Charge number 1 experiences two repulsive forces. There's a repulsive force this way caused by number 2, and there's a repulsive force the same direction caused by number 3. They combine together to give me that red force, that red dotted line force that you see. That makes sense? F2 is to the left, F3 is to the left. Together they give me a bigger force to the left. Charge 2, on the other hand, experiences a force to the left caused by number 3, and a force to the right caused by number 1. Why is the force number 1 bigger than the force caused by number 3? Yeah. Because number 1 is closer, right? Number 3 is further away, the force is going to be smaller. The force on number 3 is caused by a couple of forces. The force caused by number 1 and the force caused by number 2. Both of those are pretty small forces, giving us a pretty small net force, because, like I said just a second ago, our distance is pretty big there, right? Small forces with big distance. All right, that's not in static equilibrium. Forces are not balanced. I want to focus on charge 2. What's going to happen to charge 2? What's going to happen to charge 2? There's two forces, one caused by 3 and one caused by 1. Where's it going to go as a result of those two forces? So which direction, left or right? Good. It's going to go to the right because the force to the right is bigger. Now, as it goes to the right, what's going to happen to the value of F1? As it moves closer to charge 3 and further away from charge 1, what's going to happen to the value of F1? Michael? It's going to decrease. So F1 is going to get smaller, and F3 is going to get bigger. Good. At some point, F1 and F3 will be the same value, right? Now you're in equilibrium. This thing is not going to move anywhere now because the forces are balanced. That's static equilibrium. What does that diagram look like, or the distribution look like? Well, once again, the charge is going to be on the surface. And once again, they're going to be evenly distributed. So it looks like if you have a uniform shape here, whether it's rounded or flat, the answer is still the same. Charges go to the outer surface, and they're evenly distributed. No matter what the shape, as long as it's nice and uniform. Now let's take a look at one where the charges, or where the shape, I should say, isn't uniform. We've got an irregularly shaped object, or a pointy object. This is kind of pointy, right? It's pointier than the solid conducting sphere. You got a bunch of extra electrons in this thing. 4 of them, in fact. Could have 4 billion. Diagram. What's going to happen to those 4 extra electrons? What's going to happen? Well, let's label them first of all. Numbers here: 1, 2, 3, and 4. We're not even going to pay attention to 4, actually. Let's pretend 4 is not even there. We could. This makes the analysis a little bit more complicated. I want to focus on charge number 2 here. It's going to experience a force this way as a result of number 1. Great. The repulsive force caused by number 1. It's going to experience a force this way caused by number 3, right? So we got two forces here that don't directly, Derek, oppose each other. Right, Derek? They don't oppose each other. Kind of. I mean, one goes to the right, and then one goes up and to the left. So there's a little bit of opposing forces, but not directly opposing. We're going to break F3 down into, we'll call it X and Y components. We'll pretend this is our x-axis, this is our y-axis. We'll break it down into X and Y components. Now we can see that the only Y component we have in this entire analysis is the Y component of F3, which pushes it outward. So, once again, just like the last two diagrams, the charges are going to go to the outer surface. So what's the distribution of the outer surface going to look like? Take a look at the value of F1 and the X component of the value of F3. F1 is bigger, right? So what's going to happen to this electron? It's going to go closer to the tip, because the force that pushes it closer to the tip is bigger. As it goes closer to the tip, F1 gets smaller, and F3X component gets bigger. So at some point they're going to balance. But when they balance, this time, 2 and 3 are going to end up closer to each other than 1 and 3. So in other words, the effect that we get here is that these charges will go to the outer surface, but they're not evenly distributed on the outer surface. There's a higher concentration of the charges where it's pointing. Why do you think when you walk across the carpet and you go to touch somebody to give them a shock, why do you think you don't touch them with the side of your arm? Why do you not touch them with your hip? Why do you not back up to them and touch them with your back? It doesn't work very well to shock somebody with your back. Right? Why? Why does it work better to shock somebody with your fingertips? It's pointy, right? It's pointy. It's smaller surface area of pointing. Pointing at things have a higher concentration of charge. When we use the static bulb, the very first day of this unit, why did your hair stand up on it? Because your hair is pointing. And there was a higher concentration of charge of electrons in your hair than there was in other parts of your body. That caused the hair to repel each other because it was a higher concentration of electrons. And it stood up, at least a little bit. Why do you think lightning rods are pointed? When you see a lightning rod on the top of the building, it's not this flat thing or this ball on the top of the building. It's a pointy thing at the top of the building. Because we have a higher concentration of charge there than we do on the ground. Yep. Charge 1 does affect charge 3. It absolutely does. I'm only looking at the force on charge 2 right now. We could do the same analysis with charge 3 though. If we looked at the force of charge 1 on charge 3, okay, or charge 4 on charge 2, then we would find that it would point this way, right? So there would be an additional force pushing it out towards the tip, and an additional force pushing it to the outer surface. So it would just magnify the effect. I just wanted to simplify that here a little bit, but we get the exact same thing. But absolutely, it does affect it. There's another 50,000 million charges that would affect it as well. It just makes, the more arrows we have drawn, the more complicated that is. Good question. Last one that I want to go over here today, guys. A hollow conducting object. Listen, this is identical, the analysis of this is identical to the first one, a solid conducting sphere. When we have a hollow conducting object, where do the electrons go? They go to the outer surface. How are they distributed? Evenly. So why did I make this a separate one over the first solid conducting sphere that we drew? Because I want to look at something else, the electric field inside the hollow conducting object. The electric field caused by the first charge is going to be toward the charge. The second one is going to be toward the charge. Third one is going to be toward the charge. What do you think happens when these three electric fields get added vectorially? If we broke them down into epsilon components, what would the net field become? 0. Good. It becomes 0. What does that tell us? Inside a hollow conducting sphere, doesn't matter where we are, the analysis is easier in the middle, okay, but in the end, the net electric field anywhere inside that hollow conducting sphere is 0. Anywhere inside that sphere, if the field is 0, then the force on any other experiencer has to be 0 as well. In other words, it doesn't matter how much charge is in this thing, inside this thing, there is absolutely no electrical effect. Which means everything that you've always thought about cars and lightning storms, right? You always heard that expression, cars are safe to be in a lightning storm, right? It is. It's true. A car is one of the safest places to be in a lightning storm. But it's not because of the repairs that everybody's thinking. Lightning just came down from a cloud to your car. You don't think it's going to happen at your cover to go to the ground? Of course it can. Of course it can. And it does. All the time. Lightning strikes your car. Well, lightning doesn't strike cars all the time, but it can. It strikes airplanes all the time. Why are we safe? Airplanes don't have rubber tires, or at least not touching the ground. Why are we safe inside an airplane or inside a car? Because the net field inside the conductor, the airplane or the car, is 0. As soon as you start making airplanes out of plastic, then we got a problem. We probably have a lot of problems as soon as we start making airplanes out of plastic. But one of the biggest problems is getting struck by lightning. Airplanes get struck by lightning all the time. They're pretty high up, right? And they're going right through these rain clouds. They get struck by lightning all the time. A lot of times, you may have even been in one. Struck by lightning, you may not have even known it. Because there was no electrical effect inside. Yeah. Well, if we compare the plastic, that's a good question. If we compare the plastic, you don't have a conducting surface. So the net electric field isn't going to be 0 inside. So if you have, you're sitting inside your plastic car, and you can get electrocuted because the net electric field isn't 0 inside your metal car, which is it seems ironic, right?
It seems like, oh, you want to get as far away from metal as you can. No, you want to get inside metal. You can start violating Remington anyway. Inside the